so today we are going to continue discussing finite volume. So on Monday, we started on finite volume schemes by analyzing how the solution of a scalar one-dimensional conservation law should look like. Right? We discussed the continuous regions of the solution where the solution follows straight lines we call characteristic lines. Along characteristic lines, the solution doesn't change. du dt equal to 0. So they are constant. They are contour lines in the space-time plot. We also analyzed discontinuous regions we call shock waves. The shock waves is basically a jump in the solution. And we also can analyze the speed of the shock wave as it propagates over space. Characteristics of the slope of the characteristics and the slope and the speed of the shock waves has a commonality. So dx dt is equal to df over du in smooth regions that is we call characteristic lines. And the dx of the shock wave dt would equal to what? What is the speed of the shock wave? It is delta f over delta u. All right. df du can really be seen from analyzing the differential equation. This is the conservation law. And that can be transformed into another form. Basically, df du times partial u partial x equal to 0. What form is this? It's called the primitive form. And this df du looks like an advection speed. Right? From that, you can remember, okay, this is the slope of the characteristics. That's how fast the characteristics travel. And the generalization of that is basically how fast the shock wave would travel. Instead of df dt, a differential, it is a delta f over delta u. It is a finite difference. And in the special case of Burger's equation, this delta f over delta u is basically is the average of the characteristics on the left side and on the right-hand side of the shock wave. All right, that's what we have looked at in terms of the analytical behavior of conservation laws last lecture. We also started to look at finite volume schemes. So first of all, finite volume schemes tracks cell averages. If you use finite volume schemes, your solution looks pretty much like that. So it's like you can think of it, you can visualize it as piecewise constants, but like we actually don't have any functional approximation of the solution. We just store the cell averages. Okay, the actual solution may look like this, but it should have the cell averages stored in your computer. So let's say we have the first cell, second cell, third cell, etc. And the cell interfaces are identified by 1.5, 2.5, etc. These are the interface points. And the finite volume scheme basically says that the dui dt, these are the cell averages, okay, is equal to d dt. And if I write down the definition of the cell average, I delta x, I plus 1 delta x. Well, let me just write it as a little bit more generalized. This is x of I minus half. This is x of I plus half. These are the location of the interfaces. Remember, the half points And now of secondary importance, they are the location of the grid points. Of primary importance are the cell averages. So the cells themselves are identified with integers. That's completely opposite from the finite difference schemes. And the grid points are fractionals. And these are the grid points. So average of u dx, this is the definition of ui bar. Okay. And if we follow the integral form of the differential equation, which is the only form that we should count on in the presence of discontinuity, all the other forms is no longer reliable. I mean, the spatial derivative doesn't have to exist in the solution. So we count on the integral form, and in one dimension, that becomes d dt of delta 1 over delta x is still here. Okay, 1 over delta x. Oh, okay. Sorry, d dt is no longer here. D dt is put into this, and after the transformation, we have u on the xi plus half and xi minus half. Right? Normal is pointing outwards. That means I have a negative sign on this. Right? Did I make a mistake in signs? No? Okay, I'm fine. Okay, or this is equal to u at, let me write it this way, u at x minus half minus u at I plus half. Oh, this is f of u. I'm sorry. This is f of u, right? The integral form is f of u. The integral form is d dt of integral L and R u dx plus f of u R and L equal to 0, right? So this is the integral form of the differential equation. This over delta x. And this, the flux at the grid points where the cell interfaces needs to be approximated with numerical flux.